Is Yasuhiro Hatsugai from University of Tsukuba, Japan, and he will be talking about molecular orbital construction of flatbands and applications. So please, the screen is all yours. You have 30 minutes.
Okay, thank you. So thank you for introduction. So let me also starting by thanking the organizer for giving me a chance to talk about our recent work. So this is my title of today's talk. So that will be molecular orbital construction, which we are focusing on recently. So this is the plan of this today's talk. So let me give a very short introduction of the flat band. And the next thing I will explain our way of construction of the flat band. That's molecular orbital thing. And I'll give you three applications. One is related to randomness. And another, second one is related to some chemical compound called the MOF or COF. And the third part is related to the introduction. Okay, maybe everybody may know this long history, but let me give you some little bit idea about the flat band. Maybe one of the most oldest examples of the flat band can be Weierstrass model in 91. Anyway, there's several flat band in tight band model. And the another old one can be given by Dangote-Frazaki model related to the single Dirac Freemion thing. Anyway, they discuss some lattice model, and actually there appears some flat band. That's kind of the reason for the breaking of the Nielsen-Meyer theorem, but I don't want to go into detail. But anyway, there's a flat band appears in this paper. And the maybe one of the most important origin of the flat band can be related to the flat band ferromagnetism. And the Harutasaki and the Rip and Miyauke gave some several series of paper related to the ferromagnetism. That's also very old. And the another kind of the flat band, but may not be in a legal sense of the flat band related to the Penrose tiling, because the Penrose tiling is not periodic. So in a legal sense, this is not a flat band, but there are some macroscopic degeneracy that's closely related to our flat band molecular orbital construction also. And that's applied to the dice lattice by Sutherland just a little bit later. And in some sense, the Dingran edge state of the graphene can be related to the flat band thing. But the point is that to have the flat band, there should be some reason. And the most famous explanation can be the line graph explanation. But we are trying to give some another reason to describe the flat band that's related to the molecular orbital thing that I want to explain now. And we have wrote several papers about this flat band by molecular orbitals that MO thing. The original idea is about 10 years ago. That's quite a little bit old. And in 19th, there's a kind of very important one more step by Tomonari Mizoguchi. He's a young our colleague. And after that, we could proceed several things. And the one is a randomness thing, and the another one is the MOF and COF thing, and the final one is the interaction. So I will explain this thing today. Okay, let me start by explaining this molecular orbital thing. That's really a chemical thing, a molecular orbital, sp3 or sp4, or sp3 or sp2, everybody knows that. That's really related. So to explain this, let me just start from the very famous Kagome flat band, like this. This dispersion can appeared in the previous talk also. There's a flat band of energy -2, and the Hamiltonian is 3 by 3 is given by like this. This is all. So I want to explain why there is a flat band at -2. So the simplest the observation is that if one adds 2 times 3 by 3 identity matrices, this H plus 2 E3 has a k-independent eigenvalue 0. That's clear, right? This flat band at -2. So it means there's some vanishing eigenstate zero vector that are 3 components like this. This is the case. So the reason to have this one is that the by the simple observation, because this H plus 2 E3 is decomposed into very simple form like this. It can be just directly checked by this very simple manipulation. So if one has this kind of decomposition, the why this zero wave function exists is very clear, because to have the zero mode, this zero state is orthogonal to this 1 and 2 by these two equation, and then it's clear that here this zero state is a zero mode of the Hamiltonian like this. And actually there are two equations for 3 variables, V1, V2, V3. So there should be one non-trivial solution. That's one flat band. That is our reasoning of the zero mode flat band. Okay, and if one knows this story, one can easily generalize this one. One can put some extra factor, T blue and T red like this. This is a breathing Kagome. It's trivial. The reasoning is the same. But it can be also simply generalized to this 1 prime and 2 prime. That can be any like this. Still, we have a flat band at equal 0. And the one more observation is that if this 1 prime and 2 prime is proportional, then only one condition is enough. So in this case, 3 minus 1 equals 2, and 2 zero modes should appear. That really occurs at the gamma point of the Kagome, because if K1 and K equals 0, then this 1 and 2 is the same. So this story applies, and one can have extra band touching here. Okay, this is a simple reasoning. And then it can be easily extended to the one more dimension. That's a 3D pyroclover, actually. Then one can extend into the breathing pyroclover by the simple reasoning. So in this case, the dimension is 3, so 4 components. So we still have just 2 molecular orbitals. We have 4 minus 2 are 2 zero modes flat bands. And if this 1 prime and 2 prime are proportional, then one have 3 zero modes. That's extra band touching. And one can do the same thing in any dimension, but I don't want to go into detail. And a little bit more simple generalization, but quite powerful, was done with discussion with Tomonari in 90s. This is the original Kagome case, but this is not a kind of general. So we can generalize into a little bit more thing like this. So even for this matrix generalization or the hybridization of the molecular orbital, we still have the same story. So we still have the one flat band in the case of the Kagome and this generalization. It's very simple, but quite powerful. Because one can do the same thing in real space like this. So this first part, this is just a usual tight binding Hamiltonian by atomic orbitals. This NK is just atomic orbital. And one may include a spin also. And if one do the same thing by a molecular orbital I of this valencies, and this I is just the linear combination with the atomic orbital like this, which we call the molecular orbital, because this hydrogen molecule case can be very famous, right? So there can be a 2 atomic orbital H left and H right, but by the adding and subtracting, one can construct molecular orbitals. In this sense, our construction of this I state is the same to the molecular orbital of the hydrogen atom. So we call this the molecular orbital construction. So as for this molecular orbital hopping Hamiltonian, if this number of molecular orbital m is less than the number of atomic sites, like this, then we should have the 0 eigenstates. That's non-trivial. due to the by the same reasoning. So in this case, one should have a zero or the zero mode, and that should be generically degenerated, and this degeneracy can be n-1. And this is in real space. So one can easily include the randomness. And if these molecular orbitals are periodic, one have the degenerate flat band. This is a simple reasoning. So in some sense, if this molecular orbital is less than the number of atomic sites, if the physical meaning of that is the degeneracy is not enough, then some states are localized. That's the origin of the flat band. Okay, and maybe just I want to show you some example. So if one consider this kind of a little bit complicated lattice system in 2D, if one constructs molecular orbital 1 like this and molecular orbital 2 like this, one should have a flat band like this by the same reasoning by a molecular orbital hopping Hamiltonian. Okay. So in this sense, one can do the same thing with randomness. That we call the random molecular orbital model. So we have two kinds of the molecular orbitals, but that can be random. But in this case, the total number of the molecular orbital is less than the total number of atomic sites. So there is some macroscopic degeneracy like this, and I don't want to go into detail. But anyway, this zero mode wave function is quite spiky and very special. And that reminds me some very similar behavior of the flat band system. This is some typical the reference is diffused here, but I don't want to go into detail. But the point is that one can apply this random molecular orbital thing. Okay, so next topic is the COF thing. That's called the Covalent-Organic Framework or metal organic framework thing. Actually, I'm not so much specialist for this material, but yeah, we learn a little bit about the work of the flat band. Let me explain this. So this is a typical example. We call that the polymerized triptychs. So this is a COF, covalent-organic framework. So the building block of this material is this triptychs molecule like this. This is like this kind of thing. This is called the linker. And the another building block of the polymerized triptychs is the phenyl molecule like this. So this is called the linkage. The point is that using this linker and linkage, one can make a 2D network material, COF, and that's like this. So this the blue triangle is the triptychs molecule. This pink part is the phenyl. So this the triptychs is the linker, and that connects linkage thing. Linkage is phenyl. Okay, and there's some first principle calculation, and I was taught this material from my colleague Susumu Okada, and they did some first principle calculation. But the point is that there are a set of flat bonds in many places like this. And they also did some tight binding calculation, but we also repeated this tight binding calculation and got some little bit interesting thing. So this is a tight binding model. We model this phenyl, this C6 molecule to the point, single orbital approximation. Okay, so this is a tight binding band structure. This can be quite simple. Actually, there are 9 independent orbital, 1 to 9. So there are 9 bands. And you can see there are several flat bands, 3 flat bands actually like this. And this T is the hopping of this triptychs thing. So this is blue hopping. And this red line is the hopping inside the linkage. That we call put T prime. And this band structure is a T, and T prime is 1 and 2 case. So in this case, flat band position is given by like this. And there's some reasoning actually. So this flat band position is just given by a three-site problem, just a three-site molecule like this. But we need to put a little bit extra potential at the boundary. But if putting this extra potential, if one diagonalize this three-site problem, one can get the position energy of the flat band. That's this and this and this in this case. So let me explain this reason a little bit in this busy transparency. So this is the momentum-dependent band Hamiltonian in momentum space. And this momentum space Hamiltonian is given by a linkage Hamiltonian, three linkage Hamiltonian, this guy and this guy and this guy. And the two linker Hamiltonian, this H upper triangle and H lower triangle. And this upper triangle Hamiltonian and the down triangle Hamiltonian, linker Hamiltonian can be given by is written by a molecular orbital by 1, 2, 3. 1, 2, 3 is this guy. And 7, 8, 9 is this guy. And this important observation is that this upper linker Hamiltonian is written by a projection of this molecular orbital plus some diagonal part like this. So if one puts extra condition for the state flat band condition, we call that. If one put this extra condition, this flat band Schrödinger Hamiltonian is reduced to the three independent Schrödinger equation of the localized linkages. And using this solution of the three independent linkages, one can get the flat band Hamiltonian like this. And the relative weight should be determined by this projection condition, flat band condition. But anyway, flat band energy is given by this flat band independent molecules with extra boundary term. That comes from this diagonal term. Okay. And this story can be quite general, actually. In this sense, the linkage can be any, actually, like this. And this is a kind of the model calculation. But the point is that using the analysis I explained before, actually, one can get a wave function as well. So I don't want to go into detail so much, but the point is that the flat band wave function is given by product of the Kagome that are linkers that depend on momentum, and the another part is the linkage wave function that is independent of the momentum. So the final result is that the flat band Hamiltonian, flat band wave function is explicitly written by a product of the linkers and linkage. Okay, so this is the second part 2. So finally, I wanna explain you some application number 3 that related to the interaction thing. So to discuss interaction, we need to discuss in a second quantized form. That's also very simple, but it's a little bit busy transparency. But the point is that we start from the molecular orbital, the fermion annihilation operator like this, and smaller c is just a canonical fermion, and the capital C is a molecular orbital fermion. Of course, canonical one is the simple anti-commutation relation, but the molecular one is not generically non-orthogonal, so the anti-commutation relation is not simple. But anyway, using this one can construct the let's start from the free part. So free Hamiltonian like this. So using this molecular orbital coefficient, one can get the capital H Hamiltonian of the one body thing. That's actually given by this thing. And that's given by the rectangular the matrices like this. Okay, so using this rectangular matrices, like we call that the molecular orbital matrices, the one body Hamiltonian is decomposed into this kind of form. So using this just a simple decomposition, one can easily see that the rank of H is less than M. M is the smaller part of the this rectangular matrices. So that clearly see that the at least n minus m zero mode should be appear for this H. So kernel of the H is at least n minus m dimension. This is a very simple observation, but very powerful. So maybe one of the famous example is the chiral symmetric case like this, and with AB sublattice imbalance like this. So this very famous real space Hamiltonian can be decomposed into this form. So just using this simple decomposition, the kernel of H should be greater than n minus nb. Okay, this is the explanation of the free part. And so the point is that using this the second quantized form, one can construct the zero mode fermion by Z by diagonalizing the zero mode space. This is just a canonical thing. So this Z fermion is just a canonical fermion within the flat one space. And the point is that this flat one wave function bar phi is orthogonal to the molecular orbital. So this the molecular fermion Hamiltonian capital C and this D L, that's the canonical fermion of the zero modes, that's always anticommute. Okay, that can be very simple but quite important. So using this anticommutation relation, the field zero mode wave function like this one, this is a field one body many body state by just the canonical fermion. That is a vacuum for the molecular orbital fermion C. It's just due to this very simple anticommutation relation. Okay, so using this the canonical fermion, one can calculate any the correlation function for this many body state, because that is just a simple free fermion state. But in our case, we don't need to calculate this one body fermion. That actually given by a projection of the molecular orbital fermion part. But anyway, this is a free fermion problem, so one can do anything actually. So this is not so much surprising. But the point is that this field zero mode is actually an exact unique ground state with two-body interaction. That's also kind of, in some sense, trivial. But we put a little bit special interaction H into like this. So this is the two-body interaction by molecular orbital thing. So and this interaction coefficient Vij can be any, but if one assumes this Vij is positive, and if one puts a short range interaction for Vij, this this interaction is really a strictly short range in real space, because the molecular orbital, if the molecular orbital is short range, and the point is that this interaction is positive semi-definite if Vij is positive. And we further assume this one body Hamiltonian, this part is also has positive eigenvalue, or one body energy is positive. If one assumes this one and this one can easily see that this H naught and H int are positive semi-definite both. And this zero mode or field zero mode is a unique ground state with no interacting part. That's almost trivial. And this C is a vacuum for D is a vacuum for molecular orbital fermion. So interaction part is vanishing for the applying this T. So using this three, one can see that this T is a unique ground state of the many body Hamiltonian like this. So for this state, one can calculate any correlation function easily. Okay, this is the almost last of the my talk, but one more the comment is that if one release this condition or if m is positive or Vij to be positive, if one does not put this condition, this D can be also exact eigenstate, but can be embedded in the many-body states. So that's called the quantum scar. All right. So this is all. So today I have explained you the three topics: randomness and the morph and coefficient and the interaction using a molecular orbital. That are a little bit new viewpoint. Okay, thank you.
Okay, yeah, thank you very much for the nice talk. And so now it's time for questions. Okay. Okay, I do not see any questions yet, so I will start. I actually have a question related to the randomness.
Okay.
Could you?
Maybe, for example, this one.
Yes. So could you perhaps go a bit more in detail, because I somehow understood that you still get a flat. I mean, okay, maybe I got confused. So do you have a flat band there? And then you mentioned also the
so there is a macroscopic degeneracy at zero energy. This is an integrated density of state. So actually, there's a macroscopic degeneracy here. That's a kind of flat band randomness.
Okay, but what are, I mean, what are the properties of the eigenstates? Are they still compactly localized, or you have something more complicated?
This is not compactly localized because the molecular orbital is compactly localized, but that zero mode is orthogonal to this this molecular orbital. So the zero mode is a kind of there is some tail, but of course that's short range actually. Short range, but
is it
not exactly compact localized? So support is finite, is not finite, but exponentially localized.
So it's just exponential localization without. I mean, it's not multifractal or fractal. It's just exponentially localized.
That's a little bit tricky. So in a microscopic scale, that's multifractal like this. But the point is that there's macroscopic degeneracy, right? So one need to think about the trace over the all degenerate states. That makes the situation a little bit tricky. So I don't want to say that's really a multifractal, but in a short range scale, that's very spiky and the multifractal. But in a macroscopic scale, that's not like so simple. That's kind of extended due to the macroscopic degeneracy that occurs in this case. So that's a little bit different thing by the usual flat band.
So basically, so you cannot tell for sure that it's just localized or critical. It's because you have a freedom scale, how you choose this.
If one, for example, if one calculates the inverse participation ratio, that's extended. That's spread over all states like this, right? But in a microscopic scale, that's very spiky and the looks like multifractal. But in a global sense, that's not. That's due to the macroscopic degeneracy. So that's very special. So too much data degenerates.
Okay, but in principle, you could look at the generalized participation ratios and see how they scale.
Yeah,
depending on how they
scale are extended. If one calculates everything, if one considers the total system that's extended, not like a multifractal in that sense, but in a microscopic scale that's spiky and almost multifractal. But in a global sense, that's not, due to the macroscopic degeneracy. That's tricky, at least in this model.
Okay.
So maybe too much data degenerates. That's not good in that sense. But you can see it's very spiky and looks like almost multifractal, right? But not so simple, actually.
Okay. So Sergey has a question. So Sergey, please unmute yourself.
Yeah, just a follow up. So I'm still guessing around a bit. So you have here a case with disorder, and which still preserves macroscopic degeneracy.
Yes.
So then I'm still puzzled how you can. What is your strategy of now discussing properties of the eigenvectors, because you do have degeneracy, so you can mix them as you wish. So you could ask what is the most localized, right, state you can come up with, or what is the strategy? How do you analyze
this? In this case, many states are degenerate, right? So one can take only a trace is the unitary invariant. We have considered. We are discussing about the trace of the degenerate states. We did not focus on the single wave function. We have considered the trace of the degenerate wave function actually. That independent of the choice of the degeneracy. That's actually given by a zero mode many-body states. But anyway, so we consider the trace of the degenerate one-body states. So maybe this can be basically.
I think I got it. Yeah. Thank you.
I'm not sure. So we have calculated this kind of thing. This is gauge invariant, right? That's a trace over the degenerate state actually. So that the multifractal looks like thing is this one, and there are 1 point Ci lambda Ci. That's this one. So we have considered the trace over the degenerate state. Or another way to say that we have considered the many-body field zero mode wave function with randomness.
Thank you.
Okay. Chiza, please unmute yourself.
Thank you. Hatsugai, so I have two questions.
Okay.
Maybe the first one, I don't fully understand what you're mentioning about the zero mode, this random well. One thing is that it looks like you're trying to construct a Hamiltonian from the already prepared random MOs distributing over. Is it true?
Coefficient of the molecular orbital is random.
Okay, so this is going to be prepared by yourself first.
Yeah.
And you just trying to just construct an effective Hamiltonian for this random molecular orbitals.
Yes.
Is
yeah.
Correct. And then once you get, for example, for some set of such kind of molecular orbitals, you can just get a Hamiltonian that will give this kind of ground state, right? And then is it how it looks like? I mean, it looks like it's gonna fulfill the local destructive interference condition.
Yeah, this is anyway local Hamiltonian with random hopping Hamiltonian.
And the kind of random hopping Hamiltonian. Yeah. And in that case, the geometry of the Kagome lattice you have prepared is playing an intrinsic role, is it?
Yeah, the hopping is just within the Kagome hopping.
And what is going to be the restrictions? Like, I mean, once you get the Hamiltonian, there should be restrictions between the relative relationships between the T's, right?
And also there's some side potential. That's the diagonal part. So hopping and side potential are correlated by this molecular orbital thing.
In that case, there should be some kind of relationships which are not visible at the first glance. In the structure of the Hamiltonian, is it?
There's some, side potential and the random hopping is related, and the random correlated randomness. So in this case, the exact degeneracy equal 0 remains the same.
Is there any features that could be extracted from the obtained Hamiltonian for several different choices? Unique, universal features.
That's short range actually. So molecular orbital is short range, so any correlation is short range looks like very spiky, but that's short range actually. But due to the short rangeness of the molecular orbital, that's related.
Maybe I'm not properly making a question, but I was just I was wondering what is the feature of the Hamiltonian that
Hamilton, yeah.
Hamilton said once we get this kind of, yes.
So Hamiltonian is just the Kagome hopping, but that's random. And also there's some site potential, and the hopping and site potential are correlated because due to the same randomness. So that's it actually.
That's it. And then if you were able to just give a random Kagome hopping and potential models, you could always get this kind of constructions or not.
If one do this construction, we can
not before. I mean, just prepare the Hamiltonian in advance, not the wave function itself. Start from the general Hamiltonian with the random hopping of Kagome and also having a random potential. Is it always possible to construct this kind of random?
Never. Yeah, if one do this way, one can always do that.
Yeah, but this is an artificial construction. Yes, so if you do it kind of like Jesus says, of course you never get degeneracy. This is a
that's the question.
Yeah, of course, this is very artificial. But we don't need fine tuning. That's the point. So we don't need a fine tuning, but very special. I agree.
Yeah.
One more question.
Sorry, let me add.
Maybe later
go
on.
ahead.
Yeah.
No. There are no further questions.
Can I go one more comment? Just on a like linkage issue, second topic. Is it like it looks like it's very similar to what is called partial line graph by replacing one of the bonds. Like for example, if we prepare a leap lattice and just replace half of these linked connections with some clusters, it's gonna give the same connections. Is it like true, correct? In my understanding, correct?
Should be the same reasoning should be. This is another way. Just of course there is some.
Okay, thank you very much.
Mathematically, there should be a kernel is something, but this is another way to describe. So another way.
Thank you very much.
Okay. I mean, I do not see any questions yet, but I have one comment and one question. So the comment is actually related. Yes.
Okay.
Yeah, I mean, the comment is that this related to the Kagome model with on-site disorder and hopping disorder. I think there was a work by Roderick Mersner where they looked at Kagome lattice with disorder, and they showed that I think they only had probably hopping disorder, but they showed that if you correlate it, you can also get a degeneracy. But this was mostly inspired by the spin models, where you can show that if you just take a Kagome lattice with classical Heisenberg spins and nearest neighbor hopping, and you slightly disorder it, you can still maintain ground state degeneracy. And so then they simply tried to see if they can do it with the hopping model as well.
So in that case,
I have another.
Okay. Yeah. Okay. Go ahead.
Yeah, in their case, I don't remember if they had any compact states or not. I just remember they maintained the degenerate. Yeah, actually, it's related to the interacting models that you were discussing. So that's the last part.
Okay, that's quite closely related because there's some degeneracy like that. So what I have plotted here is this kind of thing today. That's actually the many body one body correlation with the field zero mode. Actually, the same thing actually.
Right, and actually, sorry, before we go to the Manybody case, I have one more question. I was thinking, what happens if you slightly detune this model? So that would correspond to taking this random molecular orbital model and adding a bit of just true random disorder. That should lift the degeneracy, and you probably and then you should be able to see what are the states. And you probably should be able to write an effective model that would correspond to a finite amount of disorders. So I'm still curious what kind of state, whether the states in this model are really extended or localized, or I mean, how do they look like? And I think one way to probably probe that is to consider a case of infinitesimal disorder.
So maybe this artificial construction is too much artificial. So if one put a little bit more molecular orbital, one can reduce the degeneracy actually. So if the degeneracy is finite, I guess that state should be a multifractal. That's my guess. So in this case, too much state are degenerated. That's not good for the multifractal analysis. But if one put a little bit more randomness, if one put a little bit more molecular orbital, then one can reduce the degeneracy. And if degeneracy is finite or less than the volume, I can imagine that state is multifractal. That should be like that. So this is just my guess, but in this case, too much degeneracy makes the situation tricky.
Well, yes. Okay. So the many-body interacting case. So can you also? So my understanding is first that you can construct models with many-body models with the exactly known ground state.
That's just a field zero model, right? Like this. So this is just a field zero model, actually.
Okay. Can you also disorder these models and maintain the this property?
Yeah, if this molecular orbital C is random, say, wait a second, this one, this coefficient is random, so one can get the random molecular orbital thing like the thing before. We can still have the zero mode like this. The same thing actually. And that's almost like multifractal, but there are macroscopic degeneracy. And I have filled all of them and calculate the correlation like this. And if this one body correlation is just a random amplitude of the wave function for the random random molecular orbital case. So almost the same thing as far as the correlation function is concerned.
Okay, but I guess again the disorder. I mean, the final Hamiltonian will have disorder in it, but that disorder will be correlated.
Yeah, correlated, of course. Yeah, like this. This psi is a random matrix, but we need to have this kind of thing, like this some special form like this. If one has this kind of form, then even if this psi is random, one can have the same zero mode degeneracy. It's very simple. So very special and the special, but not we don't need fine tune. Very special, but we don't need fine tune. That's the point. Okay.
Okay. Thank you. So unless there are any last moment questions, okay, then let's thank our speaker.
Okay.